Now in this module, we will explore some properties of contour integrals. Now these properties are not new for us because we have used more or less these properties in our previous modules, but in this module we will see mathematical proofs of these properties, why these properties hold. Now our first property is, if we consider the contour C, and if it's negative contour which is minus C, then this is the relation between the contour integrals along minus C and along C. So we know that what is C. Okay, so C is just a contour. Okay, so starting from point A ending at point, okay, so let's say Z of A and Z of B. So we are moving in this direction. And what is minus C? So minus C is the same geometrical path, but we take a different direction. Okay, so minus C is going to be equal to, so this is the starting point in this case, so initial point, and we move in the opposite direction, and this is final point. So geometrically they have the same path, but the orientation or the direction of motion is different. So for example, if we take that C is you are moving from for example one city, let's call it London, to another city, Birmingham, so that's C, and minus C is going to be equal to if you move from Birmingham to London. Okay, so path is basically the same, but the orientation or direction of travel is different. Okay, so let's see how to prove this property. So what do we want to prove? If we have a complex valued function f of z, if we want to integrate it along the contour minus C, then it is going to be equal to the negative of the integral f of z along this contour C. Now let's see how to prove this thing. Now consider this parameterization of the curve C, which is z1 of t is equal to x of t plus iota y of t, and the parameter t varies from a to b. Then minus C is going to be equal to, is going to be defined as x of minus t plus iota y of minus t, and t varies from minus b to a. Okay, so now let's see why this is true. So let's say this is our path C, this is z1 of a, this is z1 of b. Okay, now if we take z2 of t to be equal to x of minus t and y of minus t, then what is going to be the initial point of this contour minus C? So to calculate the initial point, we put the first value of t, which is minus b. So let's see what is z2 of minus b in this case. So this is going to be equal to x of minus b plus iota y of minus b, which is going to be equal to x of b plus iota y of b, which is in fact z1 of b, which is the final point of this contour C. Okay, so this is final point of C. This is the initial point of C. Now what is going to be the initial point of Z2? So initial point of Z2 is when we take t is equal to minus b, and this is Z1 of b, which is the final point of Z1. So basically this is the initial point of Z2 of t, and similarly if we move on in this direction and if we calculate what is going to be the final point, so to calculate the final point of Z2 of t, we put t is equal to minus a, and we can easily see that Z2 of minus a is going to be equal to Z1 of a, so which is the final point, so final point of minus C. Okay, so once again the geometric path is the same, but the direction of travel is different. So geometrically minus C traces out the same set of points in the plane as C, but in the reverse order. So if Z1 is basically a travel from Z1 of A to Z1 of B, then this minus c will trace out the points starting from the point z1 of b. Okay, so the first point is going to be z1 of, okay, so z2 of b in this case. Okay, so the first point of the parameterization so is going to be when we put t is equal to minus b, so which is z2 of minus b, and the final point is z2 of minus a, and the direction of motion is opposite to the c. Now let's see how to prove this property. So in this case, observe that if we take z2 of minus t, then this is going to be equal to z1 of t. Now this is a very simple task to calculate. Z2 of minus t is going to be equal to x of minus t plus iota y of minus t, which is going to be equal to x of t plus iota y of t, which is definitely z1 of t. So we are going to use this relation to calculate our result. Now let's begin with the definition. So the contour integral f of z along the contour minus c is defined as minus b to a, because minus b is the first point, minus a is the final point, f of z2 of t, because that's the parameterization of the contour minus c, and its derivative d by dt of z2 of t dt. Okay, now if we take t is equal to minus s, so what's going to happen? So the limits of integration will be changed, because when we take t is equal to minus b, okay, so when t is equal to minus b, so this implies minus b is going to be, okay, so since t is equal to minus s, so the limits become, so minus b is equal to minus s, so implies s is equal to b. So the limit in this new parameter s are going to be b, and similarly when we take t is equal to minus a, then it becomes a. So the limits are translated as b to a, and similarly when we take t is equal to minus s, so it becomes f of z2 of minus s, and d by dt, so since now t is equal to minus s, so it becomes d by d minus s, because t is now minus s, of z2 of minus s, and dt becomes minus ds. Okay, so since t is equal to minus s, so dt is equal to minus ds, so that's why we get this thing. Now moving on, so z2 of minus s, we know that this is z1 of s, and ds is over here, and this minus is moved over here. Okay, and this part remains the same, so z2 of minus s is basically z1 of s, so once again using this fact. Now moving on to the next step, now we can use this minus sign to reverse these limits of integration, or change the order from b to a to a to b. Okay, so this is the property that we derived. Okay, so when we were discussing how to integrate complex valued function of real variable t. Okay, and using that property we get this answer. This remains the same. Now we want to take the derivative of z1 of s, but with respect to the parameter minus s. So this z1 is a function of s, and we want to take derivative with respect to the parameter minus s, so obviously we will be using the chain rule. So in the chain rule, we first take the derivative of z1 of s with respect to s, and then take the derivative of s with respect to minus s. Okay, now moving on, now once again using the properties of these derivatives, so this is going to be equal to 1 over d minus s by s, and we know that this is going to be equal to minus 1. Okay, so at the end what do we get? A to b, so this minus sign will be over here. Okay, f of z1 of s, z1 prime of s ds, and which is definitely equal to f of z dz along the contour c. Okay, and this minus sign comes over here. So that's how we proved that if we integrate a function along the contour minus c, then this is going to be equal to the negative of the contour integral along c. Now let's consider some examples of this thing. So there could be many examples, but let's consider some simple example. So if we want to evaluate any function f of z along this contour C, and let's say this contour is basically a circle e raised to power iota theta, and it's a complete circle starting from 0 to 2 pi. Okay, and if we evaluate this integral, and then if we evaluate this integral along minus c, so what's going to be equal to minus c in this case? So this this contour C is basically moving from 0 to 2 pi, so in other words it's moving in the counterclockwise direction. But if we take this contour minus C, which is z of minus theta, which is going to be equal to e raised to power minus iota theta, and of course the limits will be starting from minus 2 pi to 0, and of course in this case we can see that the orientation is different. Okay, so this implies, so this property implies that if we evaluate this f of z dz along minus c, then this is going to be equal to minus f of z dz along c. Now we can choose f of z to be any function. It could be z square plus 1, it could be z conjugate, it could be any other function, but this relation is going to be the same. Now moving on to our next property, if we have two complex valued function f of z and g of z, and if we want to integrate them or evaluate this contour integral along the contour C, then we are going to have this relationship that we can separately evaluate them and then we can add the answer. So for example, if f of z is basically z square, which is a polynomial, and if f of g of z, okay, so let's take g of z to be equal to z conjugate square, then what's going to happen? And we take C to be simple closed contour, simple closed contour in the plane. Okay, so the domain is the plane and the complex plane, okay, and not any other subset of the complex plane, just the entire complex plane, and C is a simple closed contour in that plane. Okay, how do we evaluate z square plus z conjugate square along this contour C? Now this is going to be equal to the integral of z square along the contour C plus the integral of conjugate square along this contour C. Now what is the advantage of this property in this case? So using some property, this integral is very simple to evaluate. So we'll see these kind of properties in our future discussions, and this integral can be evaluated separately. So these two have different properties and they have different characteristics, so that's why it's better to separate them. Now moving on to our next property, we have used it many times, but the proof of this thing is very simple. Just use the definition of the contour integral and you will be able to prove this thing. Now the next thing is, what happens if a contour consists of many contours? Okay, so for example, this is the contour C and it consists of two different contours, C1 and C2. So they are called legs of this contour. So there are two legs, C1 and C2 of this contour C. So what's going to be the relationship between the contour integral of any function along this C and these two contouring integrals along C1 and along C2? Now if we write down the parametric representation of C to be z of t, and t varies from a to b. So in other words, when we are taking z is equal to or t is equal to a, so this is the point z of a, and when we are taking t is equal to b, then this is going to be the final point z of b, and for example we are moving in this direction. Okay, and of course you can see that there is a kind of a point which is differentiating, which is dividing the contour C into two different parts, C1 and C2. So this point of course corresponds to some parameter value. So let's call that parameter value to be alpha. So when t is equal to alpha, then we get this point. So in fact this point is z of alpha. Okay, so this is alpha. So we can say that what is C1 then? C1 has the same parametric function, but the range of the parameter varies from a to alpha. So this is our C1. So this is the cut point between C1 and C2. And similarly, if you want to write down the parametric representation of C2, then this is going to be equal to Z of t, but this t varies from alpha to b. So this is the initial point of C2, and the final point is when we put t is equal to b in function Z of b. Now let's see what's going to happen. So f of z C1 plus C2 along this okay, so of this function f of z, so which is of course C1 plus C2 is C. So the contour integral f of z along C is going to be equal to, just using the definition, and since the parameter varies from a to b, so we are going to get this thing. Okay, so moving on and using the properties of integration of complex valued function of one real variable t. So using those properties, we can just write it down in as a sum of two separate integrals. Okay, so one from a to alpha and the second from alpha to b. Integrand is the same, and of course this is equal to the contour integral of f of z along C1, and this is contour integral of f of z along C2. So that's kind of give us the proof of this property, that if you want to evaluate a contour integral along C1 plus C2, then it is the same as evaluating the contour integral along C1 and then evaluating the contour integral along C2 and then adding them together. So that's once again, so we have used it somehow in our past modules, in our past discussions, but this is the proof of this property. Now our next task is to understand the effect of reparameterization of a contour on contour integral. So we know that there are many ways of parameterizing the same contour. Now let's consider a contour C with this parameterization. Z1 of t is equal to x1 of t plus iota y1 of t, and the parameter varies from a to b. And let's consider this another reparameterization of this contour C given by C z2 of s is equal to x2 of s plus iota y2 of s. Now in general, these two functions z1 of t and z2 of t are different, and the variation of this parameter is also different. Now if we represent this z1 of t in the following way, so this is the interval a to b, and when we apply this function z1 on these values of the parameter, then we get the following path C. And if we apply z2 of t on the parameter values from C to d, then we get the same path but in a different way. So it's just like two people or two athletes running from z1 of a to z1 of b, and since they are two different athletes, so their position at different time is going to be different. So one athlete represents the function z1 of t and the second athlete represents the function z2 of t, and these two functions are different and gives us different positions for different values of the parameter t and s. So in general they are going to be different, but the path that they define is going to be the same. So if this happens, then there is going to be a function h which takes a to c and then b to d, and then of course h prime of s is going to be greater than 0. So there exist such functions h, and such that z1 of t is going to be equal to z1 of h of s is going to be equal to z2 of s. Now let's go back and see what does this function do. So this function takes h of a, so applies on a is going to be equal to c, and when applied on b is going to be equal to d. So it takes a to c and then it will take to this point, and similarly it will take b to d and will take to this point. So basically it maps AB interval onto the CD interval, and then it will take us to the contour. Now if this reparameterization is given, then we have the following property, that this contour integral when taken from a to b is equal to the same, and of course the parameterization is different. Of course there could be many examples in this scenario. Now in this module we discussed some properties of contour integral which are useful in the calculation of contour integral.